Okay, let me, I think I shared already screen that I need here to get there. Up. Pointer ready. So, pointer, yeah. Okay, so now we want to continue with the age of the solar system. Where do we know information about how old the solar system can be? Well, and here we are back to these elements, uranium and thorium. They very likely were made in this cataclysmic event where the uh, material was mostly created in our solar system. So either the nova or maybe it was a neutron star merger. And now there uranium is still quite nice because uranium has two isotopes which are very long-lived. Uranium has 92 protons, and then what you see on here, 235, this is the number of protons plus neutrons, so if you subtract 92, you have the number of neutrons. It's 235, which is, by the way, the evil one that you need for a weapon. Has a half-life of about 700 million years, so big geological time scales. Uranium-238, so which has 3 neutrons more, has a half-life of of roughly 4.5 billion years. A factor of 6.5 in between. So their present abundancy ratio is 0.7. So if we the number of the 235 to total or to 238 uranium is roughly 0.7%. So if you want to run a reactor, you need about 3%. If you want a weapon, it's 20 plus. And the enrichment process is the difficult stuff. Okay. And the higher enriched, the better is the weapon, by the way. So, or the less material one needs in total. So, and by the way, so this is nowadays the ratio, but now, since the half-life are so different, if we go 700 million years back, only a bit more of 238 uranium was there, and twice as much 235. If we go 1.5 billion years ago, we have 4 times as much uranium-235, but only 20-30% more of 238. So from this ratio nowadays, what we can do, if we assume they have been created equally, and then calculate back when were they, basically when did we have the same amount of them, then we come to about 7 billion years where this event happened. If we take nuclear models into consideration in the creation in this cataclysmic event for 238 and 235 uranium, is a bit less 235 created because it fissions easier and then goes recycled to lighter masses. So fission means basically there comes a neutron, acts as an X, it cuts this big nucleus into 2 smaller ones. Then we come to roughly 5.8 billion years. So this would be the time scale, the upper limit for the time scale of our solar system. Well, what is quite a good indicator for what has been there or what is nowadays there is here on uranium-238. And then what we usually get is the decay chains or alpha particle, helium nucleus emitted, to beta decays where neutron becomes a proton, a lot of alpha decays, and then going down all the way to 206 lead, so one special isotope of lead. This is quite practical because then you look, what do you find in the isotope, the mother, at the very beginning and at the very end. And then you know how much there was at the very beginning. And for 238, 5 uranium, we have a different decay chain. We come to a different lead isotope in the end. The nice thing is every radioactive decay produces heat. And now we think, where will be this comparably heavy stuff? If you think 238 compared to carbon with 12, oh, 20 times heavier. Where will we find it? Of course, when the Earth was young and very molten, and the heavy stuff probably sank down to the center. So mostly in the center, in the core. Where you find a lot of this stuff is usually in volcanic stones. This one, or thorium, which is another long-lived radioisotope. So this is a good source, and this is usually a problem is that here in between there's radon, radioactive noble gas, likes to gas out from these volcanic stones. So one has then here, of course, then to be careful here with this, how much of this radon could gas out because of the geological structure around. Here in Scotland, a bit of a problem because you have natural stone houses or houses made of natural stone, volcanic, what means granite, and then you always get this radon gassing out. And it accumulates because it's heavier than air. It's usually at the bottom of the room. Previously it wasn't much of a problem because the windows were so cramped, or the doors, that you constantly had an exchange of air. But now the windows and doors are too good, so basically it accumulates in the house. And if you live in such a house, I would recommend you at least every second day to air properly. So switch off the heating, wait an hour until it's all cooled down a bit, and then air, switch the heating on. So no practical things for life, but we get basically from here these upper limits. A positive thing is, of course, every radioactive decay produces heat, and we have this stuff now in the core of our Earth. If you remember back, this solid inner and molten, so we need some heat source to keep this warm. Radioactivity is one of two. And here you see the heat evolution. Basically, if we say the Earth is 4.5 giga, what means billion years old. A stands for annum. The time coming now, and you see the total heating, how the power goes down. So the young Earth was obviously much warmer, and also the core was warmer, and perhaps the magnetic field even stronger then. And here's the contribution of the different isotopes. But one sees it's now fairly stable. So this heating mechanism will be there for a while. Okay. Then what we also can do, we can take rocks. Then we take there another radioisotope, 232 thorium, which has a half-life of 14 billion years. So you take an amount of this substance, wait 14 billion years, probably need to shave occasionally between. And then it's just half the stuff is still thorium, the rest is then in this decay chain down to lead. We take the amount we find, we take the amount of the decay products that we find, and then we find that the oldest rock on Earth, which are somewhere in northern Canada to be found, can be dated to be roughly 4 to 4.2 billion years. So we have a lower limit. Yet, this lower limit, of course, this is now, we have a rock where the stuff is contained in. In order to have a rock at the beginning, everything was basically more or less molten. Everything needed to have already calmed down. So this is just the lower limit. Other indicators that bring us basically radioactive, long-lived radionuclide where we could date when they were made are meteorites, shooting stars. So bigger shooting stars, not just dust grains. So this is really a bit of a solid material. And usual as everything in the solar system, they have quite a high speed. If they enter the atmosphere, this friction makes them hot, glowing. Occasionally they become so hot that burst. Most of them basically just evaporate or burn away in the atmosphere. Some of them make it down to the ground. So if they were big enough and hard enough. So for example, here is one of them. One sees the outside, basically this burned, this oxidized surface. But cutting inside, it's nice crystal structures. So they bring material to the Earth that we would say that hasn't undergone much chemical process in the last 4.5 billion years. Of course, they go through the atmosphere. They become very, very hot, and it's a question what processes are there going on? Are there diffusion processes outgoing in? Are the diffusion processes ingoing on? How much are they then totally molten, or are they just the surface hot? Yet, compared to all the other stuff that we have on Earth, they were not exposed to constantly changing conditions. And therefore better reflect what the conditions were at the very beginning of the solar system. So basically time capsules. Well, of course, sometimes they reach the Earth and they were a bit bigger. Ask the dinosaurs. Well, no longer possible really to go to the zoo and ask the crocodiles, they are dinosaurs. Or was a bit bigger. There one, I think, near Yucatan in Mexico, that is suspected to have annihilated the dinosaurs by bringing up so much dirt into the atmosphere that everything basically became dark and much cooler because the sunlight was blocked away. And then of course big ones that need loads of stuff to eat have a problem, while the smaller ones, our ancestors, well, rat-like, or rats might be big compared to them. Small ones are then better adaptable and need less food to survive. Wow. Well, so if they are a bit larger, they easily leave these impact craters behind. Happens occasionally. And what happens, this is the power of a good multiples of Hiroshima bombs. So all over the Earth we find these craters, of course. The problem with them is often on Earth, erosion. So they are there maybe 200 million years and then they are eroded and gone. On the moon, we nicely see them as they were basically. Once made on the moon, it's staying the way it is. Especially nowadays, the very young moon was also seismic active. When it was basically still rotating, then the tidal forces kept its core hot, and then you have magma, and occasionally it came to an eruption, especially on the side that was then towards the Earth. And this makes these dark spots, the seas of the moon. And there is basically magma, a different type of stone. Okay. Well, so this happens now, the Barringer crater, the Goro crater, and the Serengeti in Africa. We find a lot of them. Or where I grew up nearby, there is then this geological structure which is called the Nördlinger Ries. This is about 30 kilometers in diameter. That was about 15 million years ago. There a meteorite crashed in. And here is the second impact part. So if you ever have the chance to go there, it's quite interesting. It's relatively flat on the inside, and you have here Nördling on a bit of a spike. But this is when you take a sand, you make it flat, then you take a smaller stone and you hammer it in. You will see how the sand goes up, and then whenever it basically impacted comes down and forms a bit of a hill. The rest is relatively flat. So this was something bigger, 50 million years ago. And this area, this was Celtic Heartland. So this was where Hallstatt culture was very, very prominent. And yeah, well, here we would say this was about 100 tons of iron. But this also meant one had here lots of iron when it split up and the impact. There were lots of iron around. And this iron was now hot, going through the atmosphere. There was also carbon in the atmosphere. What happens if you make iron hot and have it in a carbon surrounding? You temper it. You make steel. And the Celts from this area were known for the very, very good steel. Or the Romans liked us to buy their spurs. So this might give us here something. You probably know these guys, and the only thing they are basically scared of, so Asterix and his tribe, is that the sky will fall on their heads. And there might be even something true, because, well, in this area you see Nördling here. If you go here, what you see is that this mountain, it's called the Ipf, or the Ipf. It used to be a Celtic hill fort. So indeed there was a lot of Celtic activity there. So, but the real impact might have been that about 500 before Christ, there was another impact. It wasn't that such a big one as here, but nevertheless it was big enough to carve basically in the, one sees there a couple of lakes, and this looks really like a meteorite explode, fell apart, and then carved in the stones, in the landscape, these lakes in. So the Starburst Lake or Amber Lake, it's south of Munich. And it created a death zone of maybe 200 kilometer long, 80 kilometer wide. So often there is something behind such scares and collective conscious. So, but as I said, the iron from this comet and the other one, It was nicely tempered, made very good steel. And nowadays, of course, these comets, if we find them, are excellent probes for science, because the lack of sedimation processes says we have still a lot of stuff as it was at the beginning of the solar system. What you see here is a probe of perhaps the best documented impact ever. This was in 2013 or so in Chelyabinsk in Russia. Meteorite that was then in the evening was on all news. This here is a bits of it. A lot of windows broke and wow. Yet there were loads of films. Why? Well, Russia, mafia state, we know it now, Godfather Putin. And the police is often equally corrupt. So what they do is manipulate the traffic lights and let you wait for 10 minutes, and when you are annoyed you just drive through, but then they check you out, find you. So that's what the major reason why many Russians have dash cams in their cars. And if you have lots of dash cams, of course, then you get everything nicely documented. So here you basically see that a couple of ratios, this iron towards magnesium, iron to silicon, of different, so that's on the Earth, again on the Earth, and then different probes from different comets. So that's how to read this. Fa, whatever Fa is, no idea. The fraction of oxygen 17, which is radioactive, which is probably made while going through the atmosphere. But I would have to read this now. Okay, so that's how we get information about these isotopic compositions. And also from the radioactive stuff that is in there, and the daughters that we find, about the age of our solar system, and we would rate it to roughly 4.5 billion years in age. Oh, that was already the age. Now, well, let's have a look through our solar system. The structure of the solar system, well, obviously we have our 4 rocky inner planets, and we have the outer planets that are gas giants. In between there is the asteroid belt. Asteroid belt had a problem. Here obviously something tried to form, but Jupiter. Every time it came too close to Jupiter, Jupiter ripped it apart. So the big rowdy in our solar system. So then of course we have the dwarf planets out here and the Kuiper belt. And further out, Oort's cloud. But this brings us to the question, why are the inner rocky and the outer gases? One explanation would be, if we look at this picture here, this burst of a solar system, where we already see basically the orbits in this accretion, or in this disk that has already formed. We see already the orbits of planets. So now what we would see here is is also inside. It's hot. The further we go away, less dense, cooler. So here it's hot. What does this mean? Where can a gas start to accumulate, to liquidify, and then maybe if it's big enough, the liquid to almost solidify, to become a massive sphere where it's cold. If it's hot, the gas would again immediately evaporate. So this is one thing we have to consider. So the gas giants rather should form on the outside, while rocky planets on the inside. So if here forms a rocky planet, and then what we also see is basically Jupiter is massive monster and compared to Mercury, tiny boy. So we would now say there was simply much more material to form the gas here, the gas giants, than the other stuff. That would be one explanation. And of course here the gas was boiled off immediately, so only the rock stuff stick together. This is the classical explanation. Yet, if one looks at simulation, one sees that basically on the outer regions the gas giants formed. But then the gas giants, basically, at least Jupiter and Saturn, they moved through this very dense soup still. What happens if a body is moving through a dense soup? It's basically slowed down. It's a viscous medium. If it's slowed down, the angular momentum drops. And therefore, the planet starts now to drifting towards the inside. So they are migrating now inside, where they collect most of the material away. So, then, why are they not inside anymore? So this inward moving is basically, they start collecting all the stuff in here. Well, here we also see basically here clearly these are bigger ones than, good, this here seems to be also a relatively big one, but who knows, maybe it's just a good collector and then immediately boils off again. Okay, and now usually we would have here the orbit due to force equilibrium. But now, of course, if the planet slows down, it gets dragged in. The centrifugal force is less, and the central force that pulls in is stronger. Okay, but then we have them in the inside collecting all the stuff. At some point they have collected most of the stuff. And now, oops. What's now happening is a second mechanism that makes them basically move outside. So there we have some kind of inverse slingshot mechanism. When they rotate, they basically collect more on one side than on the other side. That rotates away from the metal. It means now the rotation gets slowed down. If the rotation gets slowed down, the total angular momentum needs to be preserved. They go to an outer orbit again. So the same mechanism as with the moon. Moon was next week basically that it was born relatively close to the Earth, so as a drop off from the Earth, and maybe 20,000 kilometers above us. This massive moon, God, guess how high the tides were back then. Not 300,000 kilometers, 20,000 kilometers away. But now then the tidal forces, it came to this tidal locking. And then, of course, the rotation of the moon slowed down, the internal rotation around its intrinsic axis, and therefore it drifted away to keep from the Earth, or still drifts away, to keep the angular momentum, the total angular momentum as sum of this intrinsic plus revolution around the Earth's angular momentum preserved, it drifts away. Okay. The same is happening here because they had a rotation, or they have a rotation around the intrinsic axis. They collect on more one side. More is like when you cycle through the rain. Usually the front side is completely wet and the back is fine. Except you're so stupid as I with a racing bicycle with no protective, so get all the dirt from the street. But usually front side you collect that back. And if you rotate while doing so, you get certainly one side more wetter than the other, that you rotate away from it. Or what means you slow down your intrinsic rotation and you start migrating outside again. Okay, and well, what we do is we use basically similar mechanism. If the planet is moving here and we let the probe go behind it, and then of course also adjust it to its sense of rotation, it gets basically more accelerated when it goes inside than it gets slowed down when it moves away. If the planet would be at rest, this would be like racing down the ramp and a second ramp up. That is the same height, so no friction. You start at zero, you end with zero velocity. But here it's now basically the one height you start is higher than the other, because now the planet starts to drag you along in the rest frame where he's at rest. It's fine, but here it starts now pulling on you, and that's a good thing. That's basically works like a slingshot. Your arm starts moving and accelerates then in extension the stone in the sling. We use this effect. So this here is, I think, the Voyager 2, the velocity as a function of time. So, or here distance then in terms of astronomical units from the Sun. It started on Earth, and this here is the solar system's escape velocity as a function of the distance from the Sun. Voyager flew towards the Jupiter, a bit more, not directly away from the Sun, but obviously also slows down. There is also still some stuff left that slows it down, so there's always some collisions. You lose momentum. That's basically like the air resistance. Oh, then it came to Jupiter and one used the slingshot mechanism and whoosh. Again, the slowing down also because it also moves away from the Sun. Maybe not perpendicular away, because one wants to go, of course, to the planet and come close as possible to the planet without colliding. Comes to Saturn, makes all these nice pictures, but also gets massively accelerated. Starts again slowing down. Till it comes to Uranus, gets the same, whoosh. Comes to Neptune, whoosh. And at some point, 40 astronomical units. Let's have a quick look back. No, it's not shown, but I think this year was 30 to 40 astronomical units. So, stupid me, this is already. Of course, here we see Neptune is 30 astronomical units as radius from the distance from the Sun. Remember astronomical units? Distant Earth to Sun. So our natural unit for the solar system. Oh, and by now, at some point, it was measuring the density of hydrogen, Voyager. But at some point, this drastically went down. So the hydrogen basically from the solar wind, then suddenly, poof, and much less. One of the possibilities how to define, so when this heliopause is gone, to define the size of our solar system. One of the possibilities. Okay, what means when the Earth and Venus and Mars and Mercury formed, there was not so much material left also. What was left was mostly just the bigger one, or the more heavier one. And also Jupiter and Saturn had stolen most of the water. Sniff. Then you had basically this impact of ever bigger growing stuff. So every impact brings energy, makes it hot, makes the entire stuff melting. So hot melting that basically the water evaporates. Gone. No water, the young Earth. But fortunately, there were also everywhere on the outer side these dirty snowballs forming, loads of water, which then started bombarding the young Earth. So 200, 300 millions years after it formed, there was and there the moon is providing us evidence for this early bombardment. Oh, good, the large debris, the asteroid belt. Well, large debris, Ceres is a dwarf planet, same size as Pluto. So it's already considerable, but here this obviously never really formed. Every time it tried to, Jupiter ripped it apart. Oh, so Jupiter is basically the bully of the solar system. Then looking here through everything, good, rocky, we have now basically a bit this structure. By the way, these mechanisms with planets migrating as a distant function of the distance towards the solar system and back, that seemed to have happened here as well. That at some point Neptune was inside of Uranus, but then some jumped over it. Oh, well. But looking here at these pictures and the planets, then we see one massive thing, and this is the rings of Saturn. But I would later come to this here, or to the Saturn. At the moment, well, I feel like sniffing my nose. Don't want to do this to you, so I would say make here a break and do the rest in the next video.